remember from last lecture, what we did is we start with a PDE, we apply product rule, divergence theorem. Ultimately, this is the weak form. So this is really what we're after as the first step toward discretizing this and putting it into the computer as the final step of the finite element method. So here's this equation again. We've substituted in the condensed form of our natural boundary conditions. Now what we want to do in this lecture is two things. One is implement the approximation of the true solution u of x and y. Once we do that, we'll get it into a matrix form, and then we're going to talk about how do you get the functional form. So remember, before we used linear 1D interpolation functions in x. How do you do this when you have 2 degrees of freedom, x and y? Okay, so here's our approximation. We want to know our nodal solutions, and we're going to restrict ourselves to talking about Galerkin type weak form and finite element. So the functional form for the weight function is going to be the same polynomial form as our interpolation function. And for simplicity, we're going to let a naught, and f be 0. These terms just tag along. So there are cases we'll most likely give some examples later where that's not 0. But the more challenging part is getting these terms into the finite element problem. Alright, so what I've done here is I've substituted in this approximation, this weight function relation. So you notice I have that in here. So now we have all these summations you have to deal with. Well, we can write this in a more compact form, matrix equations. So you notice you have to be careful with your indices here. So you notice I'm defining this as a summing on J, both of these. This is a different indice. So you have to be very careful in how we define these. And what that leads to is the following form. So here's your weight function, partial psi sub I of x, and then partial psi sub j of x. And same thing here. Right. So if you count these indices, these go ij. They depend on the number of nodes in your problem. So you're going to sum over j for all those points, and then you're going to have these fluxes of I. So basically it gives you a large matrix of unknowns here, perhaps unknown fluxes on certain regions. And this is ultimately what we want to solve. So it becomes a linear algebra problem. And if you look at the more general case where f is not 0, these come down as additional vector that you have to deal with. So if you want to see more details on this, if you look in the book, equation 8.2, 190, nice. We put it into the finite element. Here's what those matrix equations look like. So here's your Kij. I have all these terms. Here's the more general case where you have a naught naught. Here is that force vector f sub I. So you notice here's my weight function. Same here. And you can also write it in the matrix form like this. Alright, so let's introduce this approximation function. Let's identify some rules on how do we come up with the explicit form of this function. So here are the rules. U must be continuous as required by the weak form. What I mean by that is, imagine a heat transfer problem, and if you had a problem with an interface of two different materials, the temperature has to be continuous across that interface. Alright. Another case is a flow problem. So in a flow problem, your velocity must be continuous. I'm sorry, your potential has to be continuous on the whole domain, which is not quite as intuitive. I think probably the temperature problem is the forms of this interpolation function or weight function. The other thing is it must be complete. So if the polynomial starts at the lowest order, say a constant, and then it continues increasing up to necessary order. In our specific case, that means that you need to be able to take one derivative on this. So you need what's called a C0 continuity element. Obviously, if this was a constant, it would not work. You need to have at least a linear polynomial in x and y. And then lastly, the terms in here must be independent. If they're not independent, that means that this matrix will not be full rank. If you remember from linear algebra, if this is not full rank, that means you can't invert it. It'll be singular, and you won't be able to find a solution. So that's why this has to be independent. Alright, so let's talk about the simplest element, a triangle. So here we have three nodes, so we're summing up u. You're going to sum j equals 1, 2, and 3. Before we get to that point, let's just assume that this is linear in x and y. Remember, we said we need to be able to take at least one derivative in x and y. So this is the lowest order we would expect that would work. And we've introduced three constants, c1, 2, and 3. The superscript is for each element. So for each element, you're going to have these constants. So first, let's figure out what these look like based on a given element. So imagine you got some finite element domain of your structure or system. You've got points where you put in your element. We're going to say we have scalar potentials at each node, and then you have your three constants, c1, 2, and 3, and we're plugging in values for x and y. So you get a matrix equation like this. We have this relation. We're basically invert A, and what this leads to is a form of your interpolation function. Right? So basically we get these constants. That's what we're after. Once you have that, you have it in terms of the nodal degrees of freedom, and you're done. Then we implement it numerically. You set it up the same way. So say you have some local coordinate 0 to A, 0 to B. We have this relation. I'm numbering my nodes 1, 2, 3, and 4. So if I plug in values here, I get C1, I get this relation at A0, AB, I get this, and then 0B, I get this. So again, important point is these are your nodal solutions we're after. So you have four equations, you have four unknowns, C1, 2, 3, and 4. It's a 4x4, which can be nasty to invert, but in this specific case of where your x is your x and y local coordinate, it's what polynomials look like. So you want to make sure you understand where these come from. Interesting thing to note is if you take sorry, that should be an I. So you have I, J, and that equals Kronecker delta, meaning, oh, I'm sorry. So this is psi of I. These are J. Both of these are J. If these are at the same indice, this is 1. If I and J are not equal, this will be 0. So this is Kronecker delta. It's either 0 or 1. Other thing is, anywhere inside this element, this goes for triangle or quadrilateral, if you sum up all the components It will always be 1 at any point on this. And this is just 2 cases. We could do other types of elements. You could go back to a triangle. You can add nodes in the center. You'll get a higher order polynomial because now you have 6 nodes. You can also do an 8 node. Basically you have to solve higher or larger linear algebra problems. Other thing we'll talk about later is if you shift these over to the quarter point on both sides, you'll get a singularity, a square root singularity right here, which is very interesting for very specific problems such as fracture. It becomes much more efficient than other methods to solve those type problems.